Hi, I'm Nita Jafarzadeh, and I'm going to present problem number 9, oscillating a screw for the second round of ISAC International Olympiad. The problem states that when placed on its side on a ramp and released, the screw may experience growing oscillations when it travels down the ramp. Investigate how the motion of the screw as well as the grooves of these oscillations depend on the relevant parameters. This is our overview, and let's start with the introduction. As it can be observed, the screw has two different types of motions. One of these motions is related to the rolling of the screw and the other to the slipping, sliding, and oscillations of it. The growing oscillation happens in y-axis and there is an acceleration in x-axis. This is the way that the ramp has been defended. The force analysis has been shown here. There is a gravity force that has been divided into two parts: parallel force ramp and perpendicular wave force ramp in origin system in point A and A prime. There are also inclined forces and friction forces for both of the points in X and Y axis. These are some of the data that have been extracted for the further equations. The data has been divided into two individual parts for the head and the body of the screw. And important consideration is that there are three centers of mass. The first is body center of mass, second the head center of mass, and third the whole screw center of mass. For the friction magnitude of A and A prime calculation, these formula can be used. In a perfect rolling, when the screw rotates, the distance between the center of the circle that has been created from the screw's rotation and the end of the screw is constant in the whole rotation time. We call this distance x. In this phenomenon, there is a motion close to perfect rolling. These are the data extracted and some of the forces acting on the screw on the horizontal plane. By placing the screw on a horizontal surface, if we continue the symmetry axis until it meets the horizontal surface, a cone is gonna create. Now the screw is placed on a ramp with theta angle. X is important because motions are gonna to be studied in two forms. As the screw moves down and slides, a torque applies to it, which equals to the weight of the screw multiplied by the angle that the symmetry axis makes with the surface of the ramp. Actually, X is important because we can reach torque weights. At first, we considered the screw as a cone for some, but then due to the theory, we assumed it as a cone. Frictional forces apply on 2 points on our cone. If the screw rolls on 2 wheels, AC and A prime C prime, without the slipping, the screw rotates around point O. If instead of the screw, the cone is placed on a ramp, it has this state. One time we're going to consider the motion rolling without the slipping and another time rolling with the slipping. That we're going to use the torque for the first situation and another time study the dynamical system. The cone is of polar system type that's centered around O. Because we want to investigate the situation of the symmetry axis toward the x-axis, the screw has been considered in a non-inertial origin system. So it can be studied as a O sliding as a particle in the x prime direction from O prime. The idea is that the motion consists of slipping and rolling, and the friction force can be drawn into two components. First, perpendicular to the direction, and second, parallel to the origin. At first, the movements that were only related to the cone without any slipping had been investigated. This oscillation either takes place in the I to II lane or it oscillates along this path around the x-axis. To obtain the torque, the vertical component is needed, which is obtained through mg sine theta sine phi. At first, the torque around O origin has been calculated like this, and then it has been applied to the torque equation. When the sliding is perpendicular to the axis due to this formula, isn't a constant fixed multiplication. According to the Analysis of the Rotational Motion Based on Rolling Friction and Torque article, it can be concluded that in this rotation, friction coefficient is a function of tangential velocity and it's equal to I v dots. The differential equation according to the I equation is gonna be like this. And in differential equation, the constant multiplicative has been replaced like this. If the phi in differential equation becomes small enough, this is the formula that C1 and C2 are the constant fixed multiplication. According to the screw's specific characteristics for a small angle of phi, the charts are gonna be like this with different coefficients. By increasing the phi angle, we can't consider phi's sine equals to phi anymore, so we're not able to use the previous equation and we must use this one. It happens when the oscillation angle around the x-axis is between 12 and 90 degrees. These are a part of the charts that have been obtained from the theory. This is for a case where the screw deviates to the left and right, and then when the screw becomes horizontal, it moves like an axle with two unequal wheels. The related parameters include the friction coefficient of the ram, the angle of the ram, the releasing angle of the screw, the body's length, the mass of the head of the screw, and the radius of the washer. This is the experimental setup. The size of the screws, the washers with different radiuses, and the nuts with different sizes can be observed. By increasing the friction coefficient of the ram while the number of oscillations increases, the oscillation's amplitude decreases. When the angle of the ram decreases, the number of oscillations increases, but the oscillation's amplitude decreases. When the screw is released with an angle of 0 degrees, when the ramp angle is 50 degrees, if we consider the oscillation range in the range of the screw oscillations at an angle of 22 degrees to compare its oscillation amplitude and the number of it can be said that the screw doesn't oscillate. But if we make the range smaller, its motions and oscillations will be like this. The angle of releasing the screw is one of the other parameters. By increasing this angle, it has been observed that the number of oscillations decreases, but the oscillation's amplitude increases. Changes in the screw's body's length has been investigated as well. By decreasing the body's length, the number of oscillations increases. We have done experiments with different sizes of radius as it can be observed in these charts. Oscillation amplitude in the screw with a smaller radius is higher than the oscillation amplitude in the screw with a bigger radius. By changing the mass of the head of the screw, the number of oscillations decreases, but the oscillation's amplitude increases. By comparing the charts that obtained from the experiments and theory, it can be seen that they fit well together. In these charts, a part of it doesn't fit the chart obtained from the theory. Various reasons may cause errors, including surface friction that occurs due to the non-uniformity of the surface. For example, there is a slippery spot, so because of that, the screw gonna slip different from other parts, and the result is exactly the same error in the diagram. By cleaning the surface, error reduces. This is a summary of the experiment's results. By decreasing the friction coefficient of the ramp, the oscillation amplitude increases. By increasing the angle of the ramp, the oscillation amplitude increases. By decreasing the release angle of the screw, the oscillations amplitude decreases. By increasing the body's length, oscillations amplitude increases. By decreasing the mass of the head of the screw, the oscillations amplitude decreases. By increasing the radius of the washer, the oscillations amplitude increases. In the beginning, I gave you an overview of our presentation. Then I talked about the motions. After that, I talked about the force analysis, perfect rolling, the screw in the different conditions, non-inertial system, the cone on the ramp and horizontal surface, torque, rolling and sliding, and also and the chart that we reached from the theory. I also showed you the experimental setup, the parameters, and also the charts from the experiments. And at the end of the presentation, I summarized the experiment for the comparison section. I compared the theories charts and the experiment charts, and I also explained the reason behind these errors. Thank you so much for your attention.